When investigating inverse trig functions, you have to take the original graphs and cut off certain portions of the domain in order to invert the graph and it still pass both vertical and horizontal line tests. The graphs have to have inverses that are also functions. So if you remember from college algebra, any graph that passes a vertical line test represents a function. If it also passes a horizontal line test, then it represents a one-to-one function, one input with only one output. If you read in your e-text in the inverse trig section, they will show you how they take the original graphs of sine, cosine, and tangent, mark off or cut off specific x values so that between those two values, the original graphs pass both vertical and horizontal line test. Once they're inverted, then you get the graph of an inverse trig function, which is also one-to-one, passing both vertical and horizontal line test. Now on this slide, I just cut right to it with, at the very top, y equals arcsine of x equals, and it's just another way to write it, sine inverse of x. Those two things mean the same thing. If you had trig in high school, you may have seen one form over the other, like your teacher may have preferred to always write arcsine. My personal preference is the sine inverse notation, and the same with cosine and tangent inverses. I just use the -1 notation, and it's just my personal preference. They're both equally as good. In the intro part of your homework, you're going to be asked about the domain and range of your inverse functions. Now, instead of sketching those graphs, which you can find in your e-text if you wanted to read up on them, I just go right to the portion of the unit circle that you will look in to try and find the correct answers. For example, if your problem gives you sine inverse of maybe 1/2, then you're going to look at your unit circle, and again, those are found on your Google Drive folder, but you're going to look only in the right two quadrants. Only in the right two quadrants. That's why this part is marked off. And you're going to look for the angle that would have a y coordinate of 1/2. On the next slide, we're going to get into several examples of how to actually find the cosine inverse, sine inverse, and tan inverse values. And so let's do that. We're going to jump right into some examples. Your homework will look like it's super long when you first click the link, but these problems, with the assistance of a unit circle, take mere seconds to complete. So let's go and look at some of these examples. Okay, I've set up a series of sine inverse, cosine inverse, tan inverse problems that are going to be modeled after the ones like you see on your homework on WebAssign. The sine inverse, from the first slide, and I went ahead and copied those 2 out of 4 quadrants that you'll always be looking in, just to go over an example of how you solve these. I'm going to do each one in blue and red respectively. So in blue, we're going to do the top one. When you read sine inverse of 1/2, sine inverse of 1/2, on your unit circle, sine is the y coordinate. So basically what you're looking for is what angle has a y coordinate of 1/2. If you look on your unit circle at pi/6, you will see at that angle the y coordinate is 1/2. Inverse trig functions are the angle, and specifically for sine inverse, it's the angle that has the y coordinate given in parentheses. The second sine inverse problem is sine inverse of -√3/2. -√3/2 as a y coordinate happens down here. Now, due to domain restrictions and range restrictions, that's actually a -pi/3. And that's how you'll have to report your answer. On the unit circle, it looks just like it's 300 degrees, and that's the right location. But in order to adhere to the correct domain, you actually have to do a clockwise movement, and that's why we have to report it as a negative pi over 3, so that our answers stay between positive and negative pi over 2. Moving to the next group, cosine of positive half. With cosine inverse, you look for the angle that has an x-coordinate that's given. Where's the x-coordinate of positive half? That's right, up here at 60 degrees in radians, that's pi over 3. Cosine of pi over 3 is equal to 1/2. Cosine inverse of 0. Well, what angle in these top two quadrants has an x-coordinate of 0? That's right, 90 degrees. Your x-coordinate is 0. Now, we don't want to say 90 degrees. We want to keep it in radians, but that's pi over 2. Tangent inverse on your unit circle, it's that outer ring of values that are given. Tangent is the slope of your angle. The angle that has a slope or a y to x ratio, square root of 3 is right here. If you take the y-coordinate and divide it by the x-coordinate, you will get square root of 3. Well, that angle is pi over 3, 60 degrees. But again, give it in radians. Tangent of pi over 3 is equal to square root of 3. Tangent of negative 1, in the right two quadrants, the only angle that has a y to x ratio of negative 1 is this one. On your unit circle, it shows up as 315 degrees or 7 pi over 4. For these problems, if you have a quad 4 angle, you will actually have to report it as a negative 45 or a negative pi over 4. It's a hassle, but that's just how it is if you're going to stay in the correct domain and range, specifically range. Okay, now tangent inverse from the first slide, it had a domain that was infinite. A domain that was infinite. What does that mean? Well, that means any number can be given in parentheses, and your range, which are these values, will have to be between negative pi over 2 and positive pi over 2. Now, in the first slide, I just gave you the information, but that's exactly how you interpret it. The domain is the number in the parentheses given originally. The range is the answers that you can report. Let's think back to sine and cosine. Now, they had the same domain and range. The domain was between negative and positive 1 inclusive, and the range was between negative pi over 2 and positive pi over 2. Let's think about what that means. The domain only covers, I'm going to do this and I'm going to highlight it, the numbers that can appear in the original problem. The range gives you the interval of answers that you can report. There are weird cases where your problem may say something like cosine inverse of, let's say, 5. this will be an answer that does not exist because 5 is not between negative and positive 1. And just a second example of that would be if you had sine inverse of, I'm just going to make up like negative 3. This would be another case of does not exist because you have to have a number between negative and positive 1. 5 and negative 3 are not in that interval. And so that's why you run across a few examples of problems you can't do. On this slide, we have two right triangles given with an angle theta marked. Let's also keep in mind the SOHCAHTOA acronym that we learned way back in the beginning where we did our first couple of homework links. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So we just kind of remembered the ratios with the acronym SOHCAHTOA. From where theta is marked off in the top diagram, x is opposite and 4 is adjacent. So if we're going to use opposite and adjacent, that's tangent. So the way this is built right now, I'm going to do this in blue. Tangent of the angle is equal to the opposite length over the adjacent length. Now when it comes to isolating theta, you invert your trig function. So this theta is going to be equal to tan inverse of x over 4. Your ratio doesn't change, but the appearance of your equation does. In the second example, where theta is marked, 4 is adjacent, x is hypotenuse. Which one uses adjacent and hypotenuse? That's right, cosine. Cosine of the angle given is 4 over x, adjacent over hypotenuse. Now when that translates into solving for theta, theta is cosine inverse of that ratio. And that's what the last couple of problems in your homework are going to ask you to find, is reporting theta with an inverse trig notation.